So we went from space exploration to industrial IoT. Now we get to the third keynote of the morning, which is something very personal to us, right? The human connection. And for that, we have Jamie Hamilton here from Emerge, and I'd like to introduce him with a limerick as well, if you don't mind. So Jamie Hamilton, a CTO so grand, in tech leadership, he takes a stand. With vision that's keen, and teams he'll convene, he shapes partnerships across the land. In VR and haptics, he's skilled, with talents that can be distilled. In AI and machine learning, his expertise is reassuring. He's a tech wizard, hands down thrilled. Let's give a hand to Jamie Hamilton.
Well, it's certainly all downhill from here. Thank you. I stand between you and a break, so we'll be very efficient up here. So I'm going to talk about improving human connection with MEMS sensors. And to put this mission in perspective, I talk a bit about the company. So Emerge, our mission is to build a communication platform that bridges distance and time. This is actually a picture from the wall in our office, and it reminds us what we're up to, right? So we see through here kind of the transition of tech in communication, starting at telephone and working its way through larger mobile devices. That's about when I came online. You know, through what we have today with current mobile phones. That's a PlayStation, which is another way younger people communicate through these platforms. Our mission is really to populate that last shelf. That is, come up with a better way to provide the sense of presence and connection when you can't be with the people you love. A bit about the company. So we're based in Los Angeles. We're a startup. We're about 25 people in size. The company's been founded by 3 immigrants, and so these founders had felt the pain of being disconnected from their friends and family for a long time and sought to form a company that solves that problem, that eases that pain. You know, we're proud of our diversity. We've got a bunch of immigrants and first-generation Americans on the team, and you know, we strive to have a very diverse group to help drive this vision and product. And so we are just entering the market, so we're scaling up through the holiday season of this year and through 2025. And I'll talk to you a little bit about the tech that we're building to help solve this presence problem, and we'll talk a little bit about MEMS as well as some of the sporting technologies to make that happen. So loneliness is a big problem. You know, since and during the pandemic, it really has caught our attention. Societies and countries that have aging population, it's been a focus too. Recently in the news, earlier this year, the Surgeon General actually spoke on this topic, so there's been some studies to indicate that it's a really, loneliness in general is a hazard to life expectancy. There's a lot of comorbidities, and so there was a fairly famous statement that, you know, loneliness, being disconnected from people you care about is worse than smoking 15 cigarettes a day. So and our mission is really to solve this, right, is to be able to provide better connection. Those of you that spend hours and hours on Zoom like I do, you can feel this fatigue and disconnection from people, and so this company is really leveraging immersive technology to solve that problem. We'll talk a lot about the sense of touch, so that's really one of the missing pieces in how we communicate. We've had visuals and audio capability for a long time, but again, the sense of being able to effectively communicate and feel like you're with somebody when you're not there is the problem we're trying to solve. So how are we going to do that? Emerge is invested in really taking what other companies have created very interesting and useful platforms in virtual reality and augmented reality, and supplementing that with other sensory platforms to increase that sense of immersion, as well as creating content and applications that provide the capability for social connection. So you can play games with your friends online, but you may not have that sense of communication and connection through that process because of how the applications are designed. So the product is shown on the screen. So you see an Oculus headset next to a silver-looking device. That's our product. It's called the Wave 1, and it creates the sense of touch that can be accompanied with the visuals and audio that's presented in VR. And this is a bit of an overview of how this works. So the headset that person is wearing is providing these visuals. They're seeing holograms. And what's missing really is this tactile piece, right? If I want to feel a sense of connection or presence or whatever digital content I'm interacting with, and it's almost immediately broken if I reach out with my bare hands and touch it. These devices have hand tracking on them. They're fully aware of your environment. They're very immersive, but they're missing this sense of touch. So we've built a platform that really creates tactile holograms, and then our system combines those tactile holograms with the visual holograms and allows you to interact. So in this picture, you can see the person reaching out towards that bunny rabbit. There's a graphic indicating kind of the volume of interaction that you can work with. This is a tabletop device, so the interactions and the kind of the gameplay, the user play of the device is hands down, sitting in front of a laptop-sized device, be able to interact with your friends, digital content, so on, fully immersed with applications built by Emerge, as well as you're having that tactile piece. So what we build, a large part of our team is dedicated to developing software that goes on these VR and AR platforms. We're currently on Meta's Oculus Quest platform. We'll be supporting Apple's new headset and others coming in the coming years. And our applications focus on kind of three main areas. So entertainment, we'll talk about some interesting partnerships we have. A little teaser that one might involve Yoda. We're also very much focused on providing the sense of connection and bonding and preserving memory. So in the digital realm, you can preserve these interactions that are really immersive and experience them and share them in much more effective ways than we can do today. And then on the kind of gaming multi-user experiences, we support a lot of interesting interactions, and VR obviously affords ways to play games that are independent of what you may have experienced in the physical world. So as I mentioned before, the device that we created is really creating these tactile holograms. I'm going to talk just a bit about how we do that. So the device creates force fields using airborne ultrasound. We use sensors, emitters, to create that sound. And the sense of tactility is created really by two paths. One is brute force. That is, sound is a mechanical wave. It carries momentum. When I reflect that sound off your hand, you'll feel force exerted. You can move things with this. The other is what I like to call a mind trick, and that is your neuromechanical receptors in your hand want to feel certain vibrations in certain patterns. And so the devices that we build modulate the ultrasound, the acoustic fields, the pressure fields to stimulate those neuromechanical receptors. So we give your brain and your neurological system these signals that they want to feel. That compounds with the pressure to give you the sense of tactility. So we do this with beamforming. So underneath the hood of our device is a relatively large phased array of ultrasonic emitters. That lower picture shows the PCB with those devices mounted on it. These are bulk ceramic piezoelectric transducers. We'll talk a bit more about MEMS in this moment. But by controlling the timing, the phase of those signals, the amplitude, we can manipulate the acoustic field and create beams of sound above the device. And those are really our tactile paintbrush. So you can imagine in those lower panels, so the top two panels are just showing a beam of sound moving around above the device. In the right panel, we see two of those, so that's a nice thing about phased arrays, unlike a lens, that I can create simultaneous multiple points of stimulation. And then the bottom two panels are top-down looking on that. So this is what would be going on your palm, for example. I can use this as a tactile stylus to move points of tactile sensation around. And we use these methods in various ways to create what we call tactile effects. Keep in mind, this is without gloves, hands-free, and in our applications coupled with visuals and audio that provides this sensory fusion effect that your brain wants to feel all these together. There's a fairly interesting system model at play here when we want to go to create tactility. So you can imagine you're in an experience and your hand reaches out and touches your loved one's hand. That triggers the system to say, provide the sense of touch of that hand. And then through our system, to create the signals that are applied to the phased array, there's a few different processes that are involved in. The first is really understanding where the sensation will be applied on the hand, recognizing that the neuromechanical receptors differ in different locations on the hand, as well as based on what kind of tactility you want to create. And those signals are modulated, that is, in both in space and time, to optimize for that type of interaction. That is, we map the appropriate signals based on the hand and based on what we want to feel. In addition, the antenna and phased array system model is also accounted for. So as the beam is moved around outside of the antenna array, things like the beam width change, the pressure levels change, and so the signals are adjusted to compensate for these things to provide a consistent tactile experience. We also rely on kind of time averaging effects that exist in our brain and neurological system. So if I want to create a sensation of a circle on your palm, one method that we would use would be to quickly whip the stylus around in a circle and then allow your brain to average that together with the rate fast enough that your brain and your perception doesn't recognize it's moving. So effectively, once the rates of what I call tactile painting on your palm exceed a certain rate, your brain will stitch it together as a single object, a single effect. Okay, it's been a pleasurable story so far. Now here's problems. So we currently use bulk ceramic piezoelectric emitters for our device. About 2 years ago, or 3 years ago perhaps, we started looking at alternative sensors for this. The main reason for really looking at, this is an off-the-shelf part, by the way, if we're looking out beyond this was to be able to, one, manage our COGS and cost of components much better. These devices are fairly expensive. They don't tend to reduce much with volume. There's some handcraftiness to it, to the manufacturing process, which doesn't make it very scalable for things we want to do. As well as they're really optimized for kind of pitch catch situations, proximity sensors, and so on. They do a good job with that. They're not optimized for creating tactility using ultrasound. So we invested in a MEMS program about 3 years ago to really create our own chip to do this. So we didn't see anything on the market that would provide the capability. And so we invested in developing a MEMS sensor with the hope of really solving these problems, right? So we want to leverage the, at scale, the cost benefits and manufacturing benefits of silicon processes. Smaller size is actually a big advantage for us for a lot of reasons, not only with respect to the scaling of our products, but for beamforming considerations. It gives us an opportunity to really redo the acoustic and radiation output of these antennas to suit our use case. And then, alignment with manufacturing process matters a lot, right? So when we are talking about consumer products where we're going to build tens to hundreds of millions of these things a year, the cost of PCB assemblies and the alignment of the components with standard manufacturing methods matters in terms of our overall efficiency, the cost it costs us to build it, and the value to the customer. On the right are just some pictures of, we've been at this for a while, so we've done a number of prototypes and several engineering lots, and as we'll talk in a moment, really kind of entering the volume production phase. We certainly couldn't do this without help. I'm a dummy on this stuff, and so I've learned a lot from the people that you see at the bottom and the groups that you see at the bottom of the screen. So we've worked with a lot of good teams to help really bring this up to, as I said, entering our next generation device and the next consumer device we're going to build with these sensors on board. We're marching to a start of volume production in early 2025, so we've got a lot of fun coming up next year. Just touching a bit on like what happens, how do you tell these things work, what type of measurements you make. I find this interesting given my background is in ultrasound and acoustics, but when we qualify our chips, we look at a lot of different things, not only building them up into arrays and kind of testing the tactility of it, but the qualification and verification as they get to that step has, I think, some interesting tech that's involved. So not only are we interested in kind of just the general on-wafer testing, but the acoustic characteristics of the device we characterize in a number of different ways. So you see an airborne ultrasound microphone in that top picture, as well as a motion stage, and we record the pressure waveforms and look at the kind of the resonance characteristics and the pressure these things put out. We could also measure the radiation profiles of the devices, which matters a lot to us. We use laser Doppler vibrometers to kind of measure how the things are moving and the displacements and the velocities and what's going on in the rest of the chip. The stresses here in mechanical dynamics here are quite high and interesting, as well as the electromechanical. So looking at the electromechanical resonances, all these measurements combine to help inform next designs and how we progress towards a productized chip. I'm not going to go in a lot into the details of the design. I'd like to speak a little bit about just some of the stuff I learned and what's important here. What we're really hoping is really to follow the successful path of some of the MEMS microphones and speakers, right, which have really become commodity and have changed that landscape. How is our journey different? Our journey is different really because, one, we're in the ultrasound regime, and two, we're very much in the business of pressure per dollar, as I say. And so these things are driven on resonance. The displacements and velocities are very high. So they're very aggressive sound generators. And so much of our journey through optimizing these designs and processes are managing what comes with that. The mechanical stresses are high. Your stress managing your design is really key. We've come up with some really novel ways to do that with our partners. The other key aspect we learned is the chip design with respect to the fluid dynamics matters a lot. So we're moving air around in interesting ways to create sound. And so the packaging, the back cavity, all these characteristics of the device really drive the output, right? And we kind of appreciated that as a factor, but we didn't realize how important it was until we got into it. So we've learned a lot through that process too. Managing the radiation profile and how the sound gets spit out, and your target end customer use case of what volume of tactile interaction you want to satisfy, all kind of reflects back into this into the chip design. And then details based on our design. Our design's a quad cantilever design that's pretty popular in these types of devices, and as a lot of people probably in this room and elsewhere know, managing the phase and relative timing of those cantilevers matters in terms of the effective acoustic transduction of the device. And perhaps somewhat unique to us, we build big arrays of these things, and so we're very interested in understanding how they might talk to each other. So we want really these devices to behave independently to do our beamforming correctly. So yeah, where we got to, the bottom bullets in terms of power efficiency and size and the tactility really have been validated in our use cases and our prototypes already. We're, as I mentioned, we're driving towards volume production relatively soon, at least soon in the MEMS world of timing. And so, kind of following what's happened with, MEMS microphones, for example, we're foreseeing cost reductions of 70–80% on our COGS, which is a big deal. In the consumer electronics market, of course, pricing is critical at the volumes we're doing, and so this is really an important initiative for the company. Okay, that was kind of a business high-level technical stuff, but what does it mean for tactility, for example? So, we took our characteristics of our current bulk piezoelectric system, which is kind of what I showed you earlier with those big cylinder emitters, and then based on our measurements with our MEMS devices, what we expect from our system in terms of tactility. And so we have the software versions of our system models, and we plug these characteristics in. And this slide just shows an example of what would happen to tactility in this case. We've been able to optimize, as I mentioned, the acoustic characteristics of the MEMS emitters, and optimizing the frequency as well as the radiation pattern and bandwidth allows us to really tailor the precision and resolution of what you can feel. And so the slide shows how we would paint the eMERGE logo, which you may have seen on one of these slides. Is just this wiggly thing, as all startups have a wiggly logo. But this just shows with these enhancements, you would be able to discern and create a much more compelling version of that tactile effect. So this is the challenge you have when you're giving a talk to talk about tactility. We just show it with visuals. We'll talk about a demo here in a moment that you can actually feel these sorts of things. Okay, so taking a step back, like where are we headed with this? Where is this company headed? So I talked about, we got this VR piece, we're building on the Oculus platform. We'll launch this year with products based on that. We've recently partnered with a couple of the well-known smart screen manufacturers who are really interested in taking those devices to kind of the next generation of connection. So, these companies have been very successful putting these screens with CPUs in your home, and we all stream Netflix and maybe not much more on it. So they're looking for ways to make much more interactive content. Touch could be a big piece of that. They're also very interested in providing these devices as ways you communicate with your loved ones, which aligns with some of the stuff we're doing. Apple recently announced the vision of their release of their AR headset, so that's a really interesting opportunity for us to help support some of their content and associated product launches. So we do have partnerships with Disney, as well as I mentioned the smart screen manufacturers, Sony and LG. These are great for a startup of our size to help kind of bolster our go-to-market and scale up through the next years. I can't talk a lot about Disney there and what we'll be doing with those. They're understandably very guarded on their brand, and there are certain rules when I can talk about it closer to product launch. And so to avoid Mickey Mouse coming to murder me in my sleep, we'll talk about more about this maybe around Christmas time when we can share some of the launch plans. Okay, just how do we sell this thing, right? So this is just for the business interest folks in the crowd. We're really doing a hardware-enabled SaaS model, so we'll sell the device for a fixed amount, and then there'll be a subscription on top of that. This model is really only enabled by our partnerships. I want to emphasize that. Access and collaboration with Disney and others gives us a lot of opportunities to create experiences around a lot of different franchises. And so throughout the end of this year and into 2025, you'll see us engage with a lot of different properties within Disney and some other partnerships that we're working on. So just thinking beyond, where are we going with this? So we have started with the sense of touch. With these next generation MEMS sensors, we'll have a scalable, compelling product to provide that capability to our customers. We're also investing in R&D around brain-computer interfaces, as well as smart glasses, and partnering with companies who are developing AR and mixed reality visuals. So, we envision that our goal ultimately, again, to provide this better sense of connection and immersion requires us to kind of push the bounds in these, effectively brain-computer interface type solutions. And so we see MEMS and sensors playing a huge role in these areas. So that's our team. We're celebrating our Disney partnership announcement. This is right before we got too rowdy and Mickey Mouse kicked us out. But thanks a lot for your time. And then During the break, outside next to where you picked up breakfast, there'll be, our wave 1 will be set up, and you can try some of these tactile effects. So I'll be manning that, and happy to answer any questions, and I appreciate your time.
Thank you, Jamie. Great presentation. Do we have any questions for Jamie? Tim.
Thanks, it's really exciting technology. I have a cold, couldn't shake anybody's hand. I wish I'd had your stuff yesterday to say, hey, here's how a handshake feels. How many of these PMOTs are in that device?
Yeah, great question. So the current device has 400 of those ultrasound emitters. We suspect that with the PMUT devices, we may be able to reduce that because of some of the size benefits and beamforming benefits. But it'll still be north of 200 for sure. Yeah.
And I know since you had to make your own rather than buy off the shelf, that can be a painful, expensive decision. Are you hoping other companies come up with PMUTs and you would just buy, or are you happy making your own? You even sell those as a side business?
I aged a bit through this process. Yeah, so ultimately our mission is to solve this problem for our customers. How we get there really isn't a important decision for a mortgage. So we took it on because there wasn't anything else available is really the answer. But with other companies playing more in this space, and there's been some interesting advances in some of even the bulk piezo ceramic transducers that we'll follow the solution that best solves for our end customer.
This is really cool, Jamie. I'm looking forward to the demonstration. So I'm just asking a question about future-looking kind of user experience. So I think this is really focused on hand tactile, but could I transmit a kiss to my kids through like a facial thing? Is there other views to that sort of?
Yeah. So this technology has been very focused on hand tactile experiences. We've been investigating other methods to provide kind of the sense of touch even beyond that, right? So to transmit a kiss and so on. Some of that is surprisingly difficult, partly because your hands are designed for touch and so they're very sensitive to these things, but as well as the VR systems, at least for playing in today, make some of these things difficult as well. So the systems, we rely on, for example, the hand tracking systems to know where these hands are and to facilitate some of our interactions. But what the headset doesn't know much about is what your face is really doing and these sorts. So we've got, I think we'll see bigger advances when we see some of the AR systems come out, and then the smart screen interaction devices, even though the visual parts 2D does offer a bit more flexibility in some of those use cases because you're not wearing something on your face, for example. Well, yeah, great question, Andrew.
Great, thank you.
I have a question. Do you have any recommendations for a startup that wants to develop a MEMS technology?
Be well funded is my biggest advice. So I mean, we startups we have these rose-colored glasses, right? And we're trying to solve these problems. But chip development, as well as other initiatives, are really a long-term battle. So making sure that you have investors and a board and a team that is investing in a 3-year mission or a 5-year mission to productize things are really important. We failed at that at times, so our initiative, and some of our partners that are here today know that we run hot for a bit and then we have to pause and go again, and that creates stress not only for your customers but for your company supporters and stakeholders because the timelines of things are shifting and so on. So yeah, I think being sober about what you're getting into and listening to a lot of the smart people in this room that have been down that journey before is really important.
Funding. We'll have a session on funding later, actually.
I'll bring the hat.
This is a perfect segue. Any other last question for Jamie? Yes, Kevin.
All right, you challenge me.
Please use the microphone.
The LEAP system was used for hand tracking for a CAD and systems like this. This seems like a two-way system as well. You're emitting to impact on the hands, but now I assume you could track it with much better resolution than the hand tracking systems are providing for Meta and others? I mean, there must be some two-way feedback.
So we do a little bit of that. Acoustics is kind of a bad way to do hand tracking because the return information is very specular reflections, and so it can be very difficult to always collect it. For example, emission of my hand tilts this way, I kind of lose it. And so there's some challenges there. So we combine it so we know when you're there, and we'll turn our device on and kind of know heights and things like that. But it still seems some of these IR-based camera systems like Leap are the way to go for hand tracking.
Thank you.